Alright, another draft physics video presentation. Yeah, two today. Same kind of subject, so I figure what the hell. Same video producer, same kind of argument like Veritasium, not unlikable characters, some good physics, some good science, but at the key points are shenanigans. And it's, I would argue it's deliberate. I mean, they're right in front of you, demonstrating they really don't care about the truth, they just care about confirming the propaganda. So they're going to force the results to be what the theory says instead of letting the theory prove itself with evidence. Letting the evidence take you to the truth. They're perverting it, saying it's one thing when it's something else entirely. So Veritasium did it obviously. This is sort of the same subject. He's going to get there a little different way, but it's the same idea that somehow I can shine more light on light and make the original light go away. Woo! Yeah, no, it doesn't happen. Now, Veritasium didn't go that far because he couldn't even get the part where, you get the pattern with the single photons without, rigging the experiment, essentially. And the rig was that he knew his detector was detecting 7 photons a second that weren't in the experiment. So he knew his detector was useless. Might as well get a frog to do it or get something else to detect the photons because what he's using to detect them sucks. And that was kind of obvious. And but it's the only way he get it to work is he had to take the idea of sending a single photon at a time and pretend he was staying rigid to that idea when in fact he wasn't. And and the truth is that he couldn't let the error photons pile up, so he had to do the experiment more quickly than you should do it to overcome the error rate. And that's what happened. And this experiment, this guy's going to do a similar thing. He's going to do something so obviously stupid. I mean, he's way too smart to make such a simple mistake. So it's not a mistake. It's just that he couldn't get it to work the way he should have done the experiment, and he forced it to be the outcome he wanted to show you. And so, as nice as they are, it's shenanigans. It's bad physics. It's bad science. It's being portrayed as, look at the truth is so true. Look how true it is. And it's not. And he knows it. He knows it didn't work. He had to fiddle with it and force it to work. And he doesn't say that in the videos anywhere. So nobody else apparently has forced him to put any kind of disclaimer on this video saying, oh yeah, that part was horseshit. No.
Wouldn't it be cool if there were a flashlight that instead of lighting wherever you shined it, it actually made it dark? So let me show you how we're going to do this. Would it be cool?
I don't know.
Now we can already do it.
I'd say it's pretty stupid, pretty useless. Yeah.
Cancellation technique like this, but instead of using light, we use sound. Now in this technique, let's say there's a
so we already know that sound is a completely different thing. And water's completely different too, and it won't create the same pattern in the slit experiments. None of this is the same stuff, and they just want to make everything into the same mush, and it's not the same mush, and it won't do the same things. So maybe this part of this video will be a waste of time. Maybe I should just get to the part where he's screwing with the results.
Continual sound wave producing a pattern like this. Well, what this means is that this location in space there's high pressure, and at this location there's low pressure. So it goes from high pressure, low pressure, high pressure, low pressure.
Yeah, those are real things. So that's the difference, right? High pressure and low pressure are real things. Now, when a photon doesn't have those. It just has a clump of energy and no clump of energy separated by a distance. So it's not the same thing at all, really. You can't mix 1 plus 0 and get 0. 1 is always there. 1 is a real thing. And you can't add 1 plus 1 and get 0. No, you get 2.
Pressure. Well, in order to cancel that sound, all you would need to do is produce a low pressure in the area that has a high pressure, and it would cancel out to 0 pressure. So what you do is...
Right, so again, this is just some wacky assumptions. Just, again, there's no real reason to think a photon is anything like something going through water, that it behaves anything like water, that it's moving or putting pressure. I mean, the pressure that sound creates is obvious to all of us. And the fact that water has to do with there's a big pile of water and then less water and then more water and then less water. That understanding is so obvious. Oh, if I take a bunch of water and then I mix it with a little bit of water, I'll get an average amount of water. Oh, I mean, that's so obvious. And there's no reason to think photons have plus and minus, that they have some opposite feature. That the photon is really doing on and on. A real on, or just off.
Just make an opposite curve to this. And so these cancel out, so you end up just with a straight line of constant pressure. So by adding two sounds that are out of phase with each other, then you get no sound. So now couldn't we do the same thing with light?
No.
Well, it's a little bit more...
No, you can't do the same thing with light. The truth is, because no force interacts with any force, there's no evidence that you can do it with anything, that you can bang two laser beams into each other, cause reflections, that you can bang gravity into a light, or you can bang light into gravity, or bang gravity into magnetism, or magnetism into... None of it. There's no evidence of it, except for your interpretation, your misinterpretation of these simple experiments, these simple scatter experiments.
More difficult. So light also has wave-like properties. For example, let's say we have a wavelength of...
It doesn't have any such thing. It doesn't have any properties in common with a wave beyond the idea of frequency. So you can say, oh, bullets have wave-like properties. Would that make any sense to say? Would it really make any sense to say bullets have wave-like properties? No. I mean, the fact that you can send them at a frequency, does that make them wave-like? Not the bullets.
Light that looks like this. So
is that how you would draw bullets at a frequency? Would you draw bullets at a frequency? Look, the bullets are doing this. They're not doing that in space. There's just a bullet and then another bullet and then another bullet in space. There's not doing any waves.
This wave here of light doesn't represent high or low pressure like with sound.
I mean, is that how you would draw it on, like if you're doing a schematic for your battlefield plan and sending your soldiers out, and that's how you would draw the line of soldiers as a wave, as a crooked line? No, you wouldn't draw it like that.
But what it actually represents is, at this area in space, there's a high electric field or a magnetic field, and at this location, there's a low...
Now, there just is a bit or there isn't a bit. And if the bits are in phase, you have a reconstruction of a photon. Where they're not in phase, you don't.
Electric or magnetic field. Now, the electric field goes like this, and the magnetic field is at a right angle to that coming out of it.
So he says no evidence, no proof, no reasoning, no anything for this horse crap. Absolutely no reason to believe any of this nonsense. Nothing. No good reason at all. And they'll never tell you how many of these things are, how many of these little funny, wacky things do you need to make a photon. And the polarization, that is the lumpiness of these things, is humongous. And how come there isn't two polarizations, though? How come the magnetic field has no polarization? Only the electric field does. And we don't get any answers to these questions.
But let's just look at the electric field for now. So in order to cancel this light out, what we would need to do is either get the same light shifted a half a wavelength, or have another light source in exactly the same location that produced an electric field that was completely opposite to this. Well, it's much easier to just have a light source that's shifted back a little bit. So if we could produce light coming from the exact same source that was just half a wavelength or some multiple of a half a wavelength out of phase with the source, then you could produce a light signal that looks like this.
Yeah, well, you could pulse the sources, and that might do the same thing. So, if you pulse them and then pulse them at different intervals, then your initiation point, the point you initiate the light at, will always be out of phase. So you'll be guaranteed that some of your light's going to be out of phase just by pulsing two lasers and having them pulse at the opposite rate. One on when the other one's off, the other one's on when the other one's off, that thing.
So that you end up with no light coming out of it. So the problem with doing this with light is you need your two light sources that are going to be canceling each other to come from the exact same location.
Why? There won't be any explanation for why that would be true. If it works in sound from different locations, and it works in radar from different locations, and it works from, in water from different locations, why doesn't it work in light from different locations? Why?
But last I checked, you can't get two light sources in the same location. So if I have two flashlights, I can't get one right in front of the other, or else I'll block one of them. And if I even put them close to each other, they won't be in the exact same location either. They'll be at an angle to each other. So we have to use a little trick to get the two light sources to be in the exact same spot. Well, we can actually get the two light sources to come from the same location if we use something called a beam splitter.
Right, which is a concept that's kind of, and again, not very scientific. It's called a beam splitter, implying that, oh, it just cuts it in half and sends one half this way and sends another half that way, and no difference, no other differences created. That's it. No, 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 no. It's not how it works. It's not what it does. It basically diffracts the light in one case and doesn't diffract it in the other case. One beam is spreading as it moves through the experiment. The other beam isn't spreading. Simple, deducible, absolute fact. That's a fact. That's what's called a fact that they ignore.
So what a beam splitter does is it lets half of the light go through it and it lets half of the light get reflected off of it.
Right. And how does it do that? Oh, by making a bunch of tiny little slits. By making a bunch of tiny little holes for the light to go through. What happens when light goes through a tiny hole? Oh, that's right. It goes near the surfaces, gets scattered, and spreads. Durr.
So if you turn it at a 45-degree angle like this to both of your light sources, it will reflect this one off at a 90-degree angle, and then your second light source, it will reflect off also. But remember, it lets also half the light through. So 50% of this light will come through, and 50% of this light will come through. So what you get now is two light sources coming from the...
Right, so you have a reflected source and you have a source that goes through the holes. And so the reflected source, now it doesn't spread, any more than normal. And obviously the one going through the holes, obviously that light spreads, right? That's the single slit experiment all over the place. So it's a bunch of single slits. The light obviously spreads, okay? So it's getting spread all over the place. So one source of light now is going still little straight lines, pretty straight, pretty narrow beam. And the other beam is getting this way. It's going wider and wider and wider with distance.
exact same location. So now if these two light sources are exactly equal length from this beam splitter, what you'll get is just a normal light. But if you move this even any multiple of a half a wavelength away further than this light source, then you should get some interference pattern on wherever you're shining this light.
Right, you're going to get the interference pattern because you're diffracting one set of the beam. So one set of light is changing where the photons are in space. So the simple understanding would be to the whatever. I will pause. Alright, should be back. Alright, so the idea would be after they both go through the splitter, blah, 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 blah. Well, they actually don't both go, they both interact with the splitter. So you've got one beam that's just coming straight down, and one beam that essentially goes through and back. And the point is, let me draw them this way, is one beam is hitting the reflective surface, and that doesn't cause any diffraction. That doesn't cause the light to spread or do any of that stuff. So you could say that beam is staying parallel. All the light's photons are staying parallel, and they're moving through space. The other beam, the one that went through the little tiny slits, well, that beam is going to be doing this through the whole experiment, and so it's spreading. This other beam didn't spread to the last little bit you went through, so there's a very big difference in their size. One beam is really large in space, one beam is really small in space, in terms of how much it's spread. And so you're combining those two beams on top of each other. And what they mean is that there's huge differences in the path length between the photons now. So light that was in phase is now out of phase, by whole wavelengths within this whole package of light. And that's why you get this ringed pattern, is because of the phase differences based on the spreading. So you're getting a whole bunch of pattern in here, and it's really just being caused because of this, because you've spread the light and created these longer path lengths. So the light that's here gets out of phase with the light here by wavelengths based on how long the distances you travel. The longer the distance of your mirrors between each other, the more opportunity there is to create that longer and longer path length. So, this path length would be in phase again. This path length would be in phase again. So you can kind of understand there's path lengths where it's back in phase and path lengths that aren't in phase. And that's what's causing the pattern. So it has nothing to do with the light interfering. It just has to do with where the photons are in phase and where they're out of phase based on the two different path lengths that you've created. By going through the whole experiment, the mirrors, one beam, understand, one beam goes through the beam splitter and now is spreading through the whole experiment. The other beam reflected, and so it's not spreading. And then you're combining those two, okay, by spreading the beam that didn't spread, you're only spreading for this tiny distance. The beam that was spreading, you're spreading also coming back this way. And so one of them is very wide, one of them is very narrow, okay? And all you're doing is realigning the spreads. So this is really just about, when they say that you can measure distance or the speed of light or something, or wavelengths with this experiment, you're really not measuring wavelengths. You're measuring this distance. This is what's causing the variation in what's in phase and out of phase. The wider you spread it, the more you keep changing the locations of the photons. And that's all you're doing. So you're measuring this distance. Now this is a good tool for measuring distance. The light is spreading continuously through the whole experiment, so it's definitely measuring an event that is time dependent, the spread of the light. But it's very different than measuring the wavelength of the light. So, yeah, that's probably enough of that. Camera off. Video on.
So that when you turn on one light, it's bright, but then when you turn on the other light, it actually goes darker. Okay.
So that's what he says. It actually happens. This verifies something, that they actually did do this with photons. They actually said, I can shine light on something, and then I shine another piece of light, and that piece of light makes the first light go away. Disappears. Woo, 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 woo. Bullshit. Never happened. Never an experiment. Never proven. Never demonstrated. Nothing. It's a lie. It's fake. It's phony. It's fake science. Fake news. It's just propaganda. And it's defended with desperately bad physics. Desperately bad science.
Okay, so here's what shows up on the backstop when I have one light, kind of this dim red patch. But when I turn on the other light, it gets brighter, but there's dark spots.
Right, now the reason why it gets so much brighter, 4 times brighter, right, is because there's more than one source. There's lots of sources. So when you're adding two sources, that have lots of, they already have a whole bunch of wavelengths built into them. And so you're multiplying all those sources together, and that's why it gets so much brighter when there's 2 sources.
So you can see that there's these interference patterns showing up now.
Well, they were always there. You're just now multiplying them. You're saying which beam that's being spread, the photon spread is like this in one, and the other one's like that also. So they're both like little, imagine they were both coming from the same direction. And so you're taking one and just matching another cone to another cone. And at certain locations, the cones will match with rings here, here, and here. And if I move this cone a little bit in, then they'll match in a different location. If I move it a little bit further in, then they'll match at a different location. So you're just matching 2 cones. You're meshing 2 cones and saying when are the cones full wavelengths of difference, and when do the cones have full wavelengths, of a change in distance, and a half full wavelength.
Let me turn off the other light, then turn it on. Off, on, off, on, off.
So you can see that when there was only one there, that you could see the ring pattern. And then when he adds the second one, you get this lined pattern.
Okay,
so the pattern was already there.
Now look what it looks like when I place the camera in one of the dark fringes.
All right, so he puts a hole where one of the dark fringes is, right? And he says, let me put a camera there. And this is what he's going to do. And it's just so fake and so phony. Now, the whole idea would be to have that hole where one of the dark spaces is, right? So you're on a dark, and you put a hole in. Well, what do you have to do to make a hole effective? A hole doesn't mean anything. If I stick it like this on my eye, then there's no hole anymore. Then I've just stuck my eye on the surface. I'm not sticking my eye and just seeing the light that could get through the hole. I'm seeing light from all the places that won't go through the hole. I'm seeing all of the light again. The whole point is to have the camera far enough away from the hole so the hole is actually filtering out all the other light coming from all the other wrong directions and only going to get the light that went straight through the hole. That's the whole point of the hole. He knows that, obviously. And I bet he tried to do the experiment the right way first, putting the camera behind the hole, you know, a few inches behind the hole, so the hole means something. Put the camera a few inches behind to see what gets right through the hole.
I have a hole poked here, and I'm going to put it in the dark fringe and put a camera behind that hole, so you can see what it looks like when I cover one light.
He's going to just put a hole and then put the camera right through the hole. Okay, he's not going to put it behind the hole. He's going to put it right through the hole. The hole's going to mean nothing. Just like I can make a hole in a piece of paper, right? I can make a hole in a piece of paper. I could stick the piece of paper in front of my eye, and I can say, look, I got a hole. But, you know, obviously if the hole is right in front of my eye, the hole will be doing absolutely nothing, right? It doesn't do anything if it's right next to my eye.
Versus when both are on. So you can see here that it's actually darker with both lights on.
All right, so here we go. So both lights are on. Now he's going to put a piece of paper in front. And you can see just from the fact that I can see him. I can see the room. I can see everything in the room. The camera's obviously not behind the hole. The hole is not acting as any kind of aperture. I've put the CCD, or however you want to look at it, even with the lens. I have just completely broken any idea of a camera or a lens or any of that stuff because I have put the receiving device at the same place in space as the aperture. Obviously the aperture can't cause any effect. I mean, I'm seeing the whole room. The camera has obviously been pushed right up to the edge of the hole.
I cover one light, then it becomes brighter.
And why? Oh, because you have a card and you're reflecting the light, and that's changing the exposure of the camera. I mean, it's so obvious. Yes, if you create more white light that's reflecting back at the camera says, oh, there's more light, and it changes the exposure. Ugh, I mean, this is so bad.
That's because the camera is now in the dark area, so when both lights are on, it's darker in that fringe.
Yeah.
And then when we take away one of the lights, that fringe pattern doesn't show up, and so it's actually brighter.
So we don't even see this, right, in this part, so he has to do the zoom in. So none of this happened, okay? So I'm just saying it's completely nonsense. The light never got brighter going through that hole, you know, the light that really hits that area.
With just one light. But in the areas that aren't dark, those areas are actually brighter when there's two lights on. So now here's a view of it where the camera is in the bright area of the fringe pattern. So you can see that when both lights are on, it's actually brighter. So if your point of view is actually in the right spot, then you'll see that it's actually darker when both lights are on. So when you turn on a light, it takes away light. Really cool.
Yeah, well, you can't even see it, right, frankly. I mean, I should have really blown up the video or something. I mean, I guess I watched it the first time in HD, you know, full screen, and you could see some difference here. But the fact is the difference is just being caused by the fact that he keeps changing the exposure of the amount of photons that are going into the camera. He's changing by blocking the light in the direction that causes a reflection. So he's changing how much light is going to the camera, which is causing the camera's exposure to change.
Okay, so here's my actual setup. So here are my two light sources. They're actually mirrors in this case. So in order for this to work, these two light sources have to be in the exact same phase as each other. So basically they have to behave as though they're the exact same light source.
So he's calling the mirrors a source, which is obviously kind of silly. And again, not accounting for the fact that beam splitters aren't splitting and not creating two equal beams. There are two different beams now. One beam went through little tiny holes and was spreading the whole time it was going through the experiment. The other beam reflected off a piece of mirror, and that reflection didn't cause any diffraction, any spreading, and therefore it isn't spreading through the whole experiment. And then you're taking the one you didn't spread and spreading it for the last foot, and the one you did spread, you're not spreading for the last foot. But that's it. It's spread through the whole experiment. So they're not two equal beams. This has nothing to do with waves. It's just a pile of nonsense. Nothing interferes in the space here. Photons do not interact with photons. Gravitons don't interact with gravitons. Magnetons don't interact with magnetons. Whatever you want to say, however you want to put it. Forces do not interact with forces. Forces interact with matter. Matter has to be pushed somewhere to change something.
So it's easiest to just make these be the exact same light source. So instead of having each of these be flashlights, what you do is just have each of these be mirrors. So what you do is you just shine a light from right here. The light comes up, it reflects off of here, and then comes back and passes through.
Right, and all of that isn't consequential in the same. It would be really great if that's what happened with the other half of the light, but that's not what happens to the other half of the light. The other half of the light goes to a bunch of single slits, and as we see from the single slit pattern, oh crap, that you create that huge wide blob. So the smaller the little slits are, that is, the more the more speckles of silver, the smaller the speckles, the smaller the slits, the wider the diffraction of the light. But you're inevitably, by creating any surfaces that the light has to go by, the light that goes by the surfaces is going to be scattered. It's going to be diffracted.
And the light also comes up here, it goes through, reflects off a mirror, and then hits this.
So nobody will answer this. I mean, it's a simple explanation for the experiment. It explains what's happening. It's actually happening in this stupid experiment. So for hundreds of years, they've gotten away, well, at least 100, with this preposterous explanation of what's happening in the experiment, and this nonsense about somehow, well, I can't make laser beams bang into laser beams, and the only way I can do it is this fake way of shoving it through a grating, okay, that has real properties that are going to definitely, the photons are definitely doing two different things. Reflecting and transmitting are two different events. Why do I think transmitting the light through is going to be exactly the same as reflecting it off? There's no reason to think so, but they believe so, they're going to assert so, and they're going to propagandize and distort the facts to make it look so.
And then goes this way.
And they'll never have to answer what I just said. And that's the horrible part here. Is you can't, I'm offering $1,500. $1,500, Action Lab guy. I'll give you $1,500 to address my points on your channel.
So my two light sources are actually just two mirrors right here. So you can see I can block this light source or block this light source.
Yeah, and if you would have chose differently, you'd probably get different results, right? Because if you chose the other path, it's not going to send more light to the camera, and the camera's not going to have to adjust the aperture. So, the choice makes a difference.
And then what I have here is just a lens that's going to spread out the light so we can see it better. Because this is just a laser pointer, so basically I would just get a tiny little dot. See how that's just a tiny little dot? So
yeah, one side is sending a tiny little dot, the other side is sending a bigger dot. That's the truth of it. So, and, the only ones you're going to see are the ones where they're recombined. So you're basically seeing, when he sees that dot on his finger, he's really seeing the pattern. He's seeing the rings. It's just that they're so small because his finger is so close that he can't see the rings. But he's really looking at the ringed pattern. He's not looking at one source and then the other source individually, because those would be imperceptible, almost invisible.
I'm going to spread it out with a lens here so we can see it better. It's basically the same thing that they do on flashlight LEDs. See those little bulbs on the end of the LEDs? Those are to spread out the light.
No, those are really to change the color of the light, frankly. They don't really need to spread out the light because those LEDs send light in all directions. So they really don't need to spread it. The little crap they put on top is yellow, and it's fluoresces. So they're used the blue LEDs, right? Everybody knows this. They're blue LEDs underneath, and they put the yellow crap on top to make white.
So the setup that I did here actually has a name. It's called a Michelson interferometer. And what's cool about this is the reason it interferes with each other is because those mirrors are not exactly placed equidistant from each other from the center beam splitter. And so
right. So it's just this cone matching thing. So again, as you can just, well, yeah, I'll go to the, just to be clear. All right. So just to be clear, it's two cones that you're putting back together. Okay, and so the idea would be is one cone is here, and now you're moving another cone inside of that cone, okay, but the fact is they have points that intersect, like one cone will be inside the other, so I can draw it this way, because then you can see the intersections, but I really can't, if I draw it this way, you really don't see how this cone has a center that this cone is overlapping. They both have a straight line center, and this part is mixing. The two cones are mixing here. But if I draw it this way, you can sort of get the idea. So any movement in this cone, or any movement in this cone, you could just understand that if I move it, and this line has wavelength marks on it, and this line has wavelength marks on it, you can see that as I move one of the cones, I'm going to change whether the lines match or don't match. Whether I have two lines hitting each other, or I hit 10%, 10% on both of them, or whatever, where I'm lining up the two wavelengths. So you can just see by moving one of them, I change whether this is on or off, in the sense of whether the two are in line or out of line, or in line or out of line, in phase, out of phase. So either one I can move, and I'll change which cone, which off is hitting which mark here. What mark I'm hitting with this mark will be decided by either moving either one of them. And that's all they're really doing. So they're really measuring this separation. They're not measuring the actual path length of the light, because the path lengths have been made longer. Okay, so it's not the wavelength of the light anymore, it's some longer path. And the amount of spread, that is the amount of diffraction with distance, isn't anywhere near as small. This change, the amount of distance of this spread, isn't anywhere near the size of this wavelength. So you're not measuring the same kind of differences. The spreading takes a lot more distance to create an effect than a wavelength of light. So it's not nearly as precise as they think.
If there's
I have to turn the video back on. I gotta turn this off to do that, right? Yes. Okay.
slightly off, you'll get an interference pattern. If they were exactly right, there would be no interference pattern. So what that means is if those mirrors move by any multiple of a half a wavelength of that light, then...
So again, you can kind of understand that if I'm spreading the beams and I'm using angled light, angles, that it's going to take the movement I'm going to have to do is going to be a lot bigger to change where the lines are going to switch. It's not going to be a wavelength of movement. It's going to be a lot more than that.
You'll see the interference pattern move on the background. And so you can use this to pick up the smallest, minutest movements of those mirrors. In fact, it's so sensitive that it picks up almost any movement.
So it picks up movement, picks up any vibrations, it picks up stuff, no doubt about it. But part of that's also just got to remember that the mirrors are tilting. Any tilt in the mirror, so any change in air pressure, any change in anything, will cause the pattern to change, right? If I tilt the mirror, I'm also tilting, the cone. So if I tilt the mirror, I tilted the cone. Same difference.
You can use it as a seismograph. You can use it to pick up the thermal expansion of metals. Anything that you strap that mirror to, if that mirror moves by a few nanometers, then you'll be...
Yeah, what they don't do is, like with LIGO, is they don't swing a weight, over the top of one of these experiments and prove that gravity moved a mirror. That they don't do.
Able to pick it up as a movement of those bands. In fact, in doing this experiment, even just walking around on my garage floor, which is pure concrete, if I take a step, then it messes up the bands. Okay, watch me just take a step in my garage. So that was me just slightly stepping my foot on the ground.
Right, and that might have more to do with sound. He just sent sound, and sound can vibrate objects, right? It vibrates window glass all the time. You hear sound through the glass. Why? Because the glass is vibrating. Not because the sound went through the glass. No, it's vibrating the glass and creating a new sound wave inside your house. All right, so when he's moving around or doing something, he's also creating noises, and noises hit the mirrors and move the mirrors.
This is me tapping on the cement ground. So you can see it can pick up the very slightest vibrations on the table. This is extremely sensitive. So we're picking up nanometer movements in these mirrors.
Right, says him. Okay, so I'm arguing it. Yes, it's picking up changes, and it's very good at picking up changes, but there's a difference between measuring inches and measuring meters. They're claiming they're measuring inches. They're really measuring meters.
Here. So in order to even get this pattern to be still here, I've had to turn off my freezer, I've had to turn off my air conditioning, anything that vibrates the ground slightly.
Well, I've made interferometers, and it's really not that sensitive. So he's really exaggerating here.
Will make this pattern not show up. You can see even when I just take steps on my cement in my garage, This is me walking. And I have to stand completely still, and then it comes back to normal. If I just...
Right. So, I mean, if it was this accurate, like I said, they would have used these. Why don't they use it seismically, frankly? Because they have other instruments that are more sensitive. And, so, but again, I'm not saying it's not sensitive, but this is just part of the exaggerated height. And again, his proof that light plus light equals no light is, was garbage. I mean, you could plainly see he didn't put the camera behind the hole. You didn't see the hole in the image. Clearly the camera, wasn't behind the hole. The camera was in the hole.
lift one foot up, shakes it. Even when a car drives by on the road about 100 feet away, you'll see this shake. Here comes a car. That was a car driving by, probably around 300 feet away.
Yeah, I don't buy it. So frankly, sorry. That little distance he had on that interferometer, picking up a car 300 feet away, no chance.
This is all going through solid concrete. So in this experiment, what I showed that by adding a second light in those areas that turned into dark bands, you actually had less light.
So again, he's saying that I add light to light and I get less light. And he didn't prove it, didn't show it, just keeps claiming it. They all keep claiming it happens. There's no evidence it happens. There's no good experiment that demonstrates it. It's just part of their fable. It's part of their gremlin theory, and this is how we prove it, is by shenanigans, by sticking a camera in a hole rather than behind a hole.
But in the areas where you didn't have the dark bands, you got more light. So
by using a photo detector in the Veritasium case that clearly doesn't work very well. It's just useless to use a photo detector that's picking up 7 error photons in your experiment. It's just, that's too stupid. Find one that doesn't do that.
overall, the amount of light was conserved. It just kind of pushed the light to be brighter and darker in some areas, instead of being equally spread out all over. So would it be possible to
push the light to be brighter and darker in some areas? Let me just replay that again. Because that's all it really happens, is the relative change. The brights get 4 times brighter, so of course it makes the dark look darker. But looking darker and being darker are 2 different things. So that's the thing that fools people. When something gets 4 times brighter, not twice as bright, but 4 times brighter right in front of your face, that'll make you think, hey, that dark got really dark. No, it didn't.
It just kind of pushed the light to be brighter and darker in some areas, instead of being equally spread out all over. So would it be possible to make a flashlight that does this? No, because in order to do this, you had to have the 2 light sources coming from the same location. And so if you're trying to cancel out light from this room, you'd have to cancel it from wherever these lights are coming from. And that's actually true for sound as well. We can't just block sound in all directions because the sound is coming from all directions. And so you have to block it in the direction that the sound's coming from.
But you can do it with sources that don't have to have the same path, so that's the lie. I can have 2 sources that are equal distance away. They don't have to be on top of each other. So that's the trick. Right? My fingers are here. Okay. So I can have 2 sources that are in 2 different locations as long as I have an equal distance between them. And if I have the right uneven different distance, I move one of the sources back just a little bit, then I can do the cancellation without even doing any sophisticated cancellation. So, that's just totally deceptive. It's really easy to cancel sound. It's impossible to cancel light.
So how do noise canceling headphones work then? So what we're doing is we're recording the incoming sound and then playing the opposite of that sound and blocking it out in that tiny little area over your ear. But if you try to open up that area to block a larger area, then it's harder to do because then it depends more on the angles of the incoming sound. So
it's really easy to do as long as you don't have reflections in a room. So as long as the room is big and your 2 sources are clear, it's really easy to do. You just move one speaker back a little bit. Well, you really can't just, because it has to be a single tone then. So if it's a single tone, a single 100 kilohertz tone, then all you do is move the one speaker back the appropriate amount of distance to be half a wavelength different, and then you'll cancel out the tone. So, but all you need is a clean environment to do that. Canceling out a complex wave, then you have to capture that to cancel that, because the distance is different for each one of the frequencies. So it's sort of like with light, white light. You can't cancel the fact that it's made out of the components of many frequencies. And they all have a different, they're creating rings in a different place.
Basically, the further away your two sources that you're trying to cancel out are, or the more different the angle, the less cancellation you're going to get. So for now, light cancellation is possible, but only when you have the...
So there's no light cancellation. He says it's possible. It's not possible. He didn't demonstrate because he doesn't even know what a beam splitter is and how it works. And the theory is idiotic because it is demonstrated that this doesn't work. It doesn't work for any of the forces. You just can't make a force hit a force. You have to make the force go all the way to the matter and hit the matter.
Those two sources coming from the exact same location.
Matter can only do the addition. There's no addition of forces until the matter bit gets hit, and the matter will tell you what it got hit by. But nowhere else do you have any addition of forces. Nowhere else is there an addition or subtraction. The only thing that can add and subtract is the bit of matter, an electron or a proton.
And the only way you can do that is with a beam splitter, like in this Michelson interferometer.
Right, and it's just fake and phony, and you just demonstrate how, this is what they do. This is how they engineer the truth. They don't sit there and let the experiment tell them the truth. They tell the experiment what the truth is going to be, and they force the experiment to work.
Setup. Hey everyone, thanks for watching another episode of the Action Lab. I hope you liked it. Consider subscribing if you haven't subscribed yet, and check out theactionlab.com to see the Action Lab subscription box. And thanks for watching, and I'll see you.
Yeah, blah, 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 blah. Just bad physics, unaccountable. They don't have to answer my criticisms. They can just run away. And even for $1,500, they're not going to take the free money and just, dispose of me. Say how I'm wrong. And prove that I'm wrong with some kind of experiment or some kind of argument, because they won't be able to do any of that. Because I'm actually right and they're actually wrong, and that just happens to be the truth.
Next time. Physics
isn't all this wooey crap. The evidence, if you really look at it, is overwhelming. The amount of evidence that light is a particle is overwhelming. There's so much of it. And there's just this tiny little experiment that creates a little bit of confusion. And that's it. The rest of the world, there's no confusion. The rest of the world, it's obviously rays moving in very straight lines. No curving, no bending, no bullshit. And again, the evidence, you can see it. All their arguments about light being bent by gravity, for example, you can just see it. It's so bad. The images are horrible. They're nothing. They're not mathematically correct. They're sloppy and messy and all over the place. There's clumps of stuff and clump over here. It doesn't have any of the symmetry, any of the stuff you would expect from the formulaic rules of physics. All of that they wash aside. They just say, forget it. Okay, yeah, we said everything has to be obedient to these formulas. But when they want it to be the truth, all of a sudden, it doesn't have to be that obedient. It can be way off. It's okay. Way off is cool. Anyway, so I'll probably play some more of these because these are, it's important truth, and it's important to see how you can manipulate an experiment to make it seem like or look like, but it's not the truth. And such.